So, hello my dear students, I welcome you to Chendu biology classes. So, we will be continuing our discussion on chemical bonding. So, where we have already discussed about valence shell electron pair repulsion theory and concept of hybridization, which are very important for this IIT JAM BT as well as GAT B syllabus. So, now I think we have already solved few questions which are asked from shapes, hybridization, those concepts are from related to what? Valence shell electron pair repulsion theory. I hope you are clear with that, and if you haven't watched that, so just go through the playlist of this channel in the live session so you can access all those videos. So till now I have covered periodic table and classification and questions related to that, and all the questions means from last 5-6 years if I consider. So whatever the questions asked on these topics I have covered, okay, and along with that I have provided few questions of NEET, JEE and other exams which are like correlates with the question pattern of the questions which are appeared in the GAT B as well as IIT JAM. Okay, so what are the chapters covered? Periodic table and classification, and the next structure of atom, and the next we are discussing about chemical bonding. So this is the third session on chemical bonding, I think so. Okay, so now let us begin this, and before starting this session, just look at the questions that were asked in the IIT JAM BT previously. See, this is the question they are asking: isoelectronic species among the following, like that they will be asking. I will tell you, and I will make you to solve this question by the end of this session. Okay, and look at here the molecule that shows paramagnetic nature. Okay, so I will tell you how to solve this. See here we have some compound like KO2, okay, potassium superoxide. So what is the nature? So all these things can be solved with the help of molecular orbital theory. In the short form, let us say it as MOT. Okay, and the next along with this, see, this is another question, very important it is. Yeah, so look at here, I can ask this question in multiple ways. The concept is same, but we can expect this question to be appears in multiple ways. I will show you what all those things are. Okay, yeah, so these are the things. Once after learning this molecular orbital theory, we can able to solve all those questions, and after discussing that, I will provide you few questions of NEET and JEE to practice purpose. So now what is actual use of this, what is the goal of this molecular orbital theory? So look at here, so when we have discussed about atoms, for example carbon atom if I say, so you are saying atomic number is 6, after that you are writing electronic configuration, like what you are writing 1s2, 2s2, something like 2p2, you are writing like this now. So now you are locating those electrons in respect to orbits, like orbitals. Okay, so similar to this, for molecules also we have molecular orbitals. So now we need to fill those electrons which are present in the molecule in the respect to molecular orbital. So look at here, the goal of molecular orbital theory is to describe molecules in the similar way how we described atoms. Okay, so that is in terms of orbitals, orbital diagrams. For example, you are saying S orbital, you are saying it has spherical in shape. Okay, P orbital, you are saying dumbbell in shape. Something like that. We have molecules also have molecular orbital. Atoms have atomic orbitals. In that we have electrons. The filling of electrons are taking place according to their energies, like following 3 rules. What are the 3 rules I told you? Pauli's exclusion principle, Hofbauer principle, next Hund's rule of maximum multiplicity. These things we discussed during quantum numbers in structure of atom right now. Yeah, so by following those rules only, we are filling electrons in molecules also. By following molecular orbital, energies. Okay, I will going to explain that. Okay, so this is about the main importance here. Okay, so now atoms have atomic orbitals, I told you. So for any element, for example any atom, like take any atom, so for example I am saying carbon atom. Atom means it has one nucleus, right? So nucleus, around this nucleus we have electrons revolving around it right now. So when it comes to molecules, when I say molecule, it is formed by combination of two or more elements definitely. For example nitrogen atom I am saying N. So nitrogen molecule means it is N2 it is. So it is monoatomic, it is diatomic here. So monoatomic has one nucleus, diatomic means two atoms are there. So there should be definitely two nucleus. So here there is a term here, orbitals are monocentric, whereas molecular orbitals are polycentric. What is this monocentric, polycentric? Look at here, we have how many centers? In atoms we have only one center around which electrons are revolving. Here nucleus, this molecule has either two or more than two nucleus in which the electrons are revolving here right now. So can I say molecular orbitals or molecules have polycentric, these are monocentric. Okay, clear with these basic terms right now? Yeah. So now see here you have a statement. See, according to MOT, molecule is considered to be quite different from constituent atoms. Okay, all the electrons belong to the atoms consisting in a molecule are considered to be moving along the entire molecule under the influence of all the nuclei. See here in atom, the electrons revolve around the nucleus of one atom, that particular atom. Here molecule has either like two or more than two nucleus. So the electrons of all the atoms here will be taken together, that will be moves around all the nucleus of that particular molecule. For example here I am saying Cn molecule, Cn minus, cyanide ion, it is a diatomic form only now, right now. If I say Cn, you are saying it is a molecule, so it is having respect to ion now. Okay, total number of electrons are how many? Carbon atomic number is 6, nitrogen atomic number is 7, and with one negative charge. So negative charge means one electron is extra here, so that add that electron. So total how many? So 14 electrons. These 14 electrons are revolves around the both nucleus, like carbon and nitrogen nucleus, like polycentric it is. Okay, so this is also basic thing. Now what you need to know here. See, when I told you about hybridization and valence shell electron pair repulsion theory, like molecule formation, like for example when I discussed about methane, what I told you, you have to consider the valency orbitals of central atom. What are the valency orbitals of central carbon atom here? Like you are writing 1s2, 2s2, 2p2. So atomic number 6 means total 6 electrons are there. But valency means what is the highest n value here? Ns, np we are writing now. What is the highest n value? Here it is 1, here it is 2. So n value is 2 here, highest. So these shell number, this 2 number is the highest number now. So the orbitals corresponding to that highest n value considered as valency electron. How many are there? 4. So these are 4 valency electrons take part in chemical bond formation I discussed. Okay, when it comes to hybridization. But in molecular orbital theory, all the electrons corresponds to that particular element will be taken into consideration. In normal hybridization concept, what we discussed? What we discussed there? Only valency electrons will participate. But when it comes to molecular orbital theory, all the electrons of corresponding element will participate. So it means all the 6 electrons, whether it can be 1s, 2s or 2p, all electrons are taken into consideration. I will tell you what exactly it is. So you got what is the basic difference in valency shell or hybridization concepts. We consider only valency electrons, but in MOT we are considering all the electrons. Just remember that point. Yeah. So look at here. I have atom A. I have 2 atoms. Let us say atom A I am writing atom, another atom, like N2 we are saying means 2 nitrogen atoms are there now, like that. A and A are 2 atoms. So for example, if I say orbital of this atom A has 1s, this is also has 1s orbital, right now. So this 1s orbital, this is also 1s orbital. Orbital is nothing but, how can you define orbital? So orbital is a 3-dimensional space around the nucleus where you can find electron with maximum probability. Okay. So now 1s means what is the shape of that orbital? Spherical, like this, right now. So now what I am saying, this is the space around the nucleus, finding electron is maximum. So I can represent that with something like a wave like this. Can I represent? Maximum is the amplitude, greater is the electron density in that. Okay. So this wave amplitude is there now, this depth or this height. If it is maximum, maximum is the probability of finding electron. Okay. So now take 2 orbitals. This is one orbital, this is another orbital. Now take 2 waves. This is corresponds to this one, and this will be corresponds to this one. This is 1s, let us say this is also 1s. Now if this place, and this is minus I am indicating here. See, now there are 2 possibilities. If I combine these 2 waves, what are the probabilities we have? So this positive lobe and this positive lobe can overlap right now, so that we are going to get a wave with a bigger amplitude, like this, something like this. Yes or no? With a bigger amplitude. You are adding these 2 things. Okay. Now another possibility is this positive one and this negative one. Okay. So we are going to get, see, positive negative means they will cancel out each other. So what about the resultant amplitude? That will be almost 0. It will become almost 0. Okay. So this kind of overlapping will be called as constructive interference. What is that? This will be destructive interference. Okay. So this concept is used in the case of atomic orbital overlapping. Actually this is a physics concept, waves concept. So to understand the orbital overlapping, we are using this concept here. Okay. So now in molecular orbital theory, there is a combination, there is a concept called linear combination of atomic orbital. This is a wave function I am saying now. So psi I can represent. This is another wave function for 1s. So both can overlap, like psi a plus psi a, like 2 AAs only I am saying, like this. Okay. This is constructive interference I am saying, in order to form psi AA type product. Okay, like wave. So now it can be destructive means psi A minus, like this. Like this also we can say. So this will results to form constructive, this will be giving destructive. Okay. So now just this is also psi AA I am writing. So now just square this. What is the resultant one? Like something like A plus B we have. So if you want, you can just consider this B. If you are still struggling to understand this, let take it B. It is our consideration only. Like A plus B only we have now. So tell me psi A square plus psi B square plus 2 psi A psi B we have. Something like A plus B whole square formula, it will be like this. So this is something like, if I square this, you are going to get square plus psi B square minus 2 psi A psi B. So now if you understand what I am going to explain here, just see here, when it is undergoing additive overlapping or constructive overlapping, your amplitude is looking like this. See, you have, along with this you have added this thing. When it is undergoing subtractive overlapping, see, you are doing something minus of these things. You are adding here, so that's why amplitude becomes 0, almost like decreased here. Okay. So these are the 2 ways. Now when it is undergoing constructive interference, you are going to get bonding molecular orbital. What you are going to get? When you are undergoing, when orbitals are undergoing subtractive overlapping, you are going to get antibonding molecular orbital. What is this bonding and antibonding? See here, when 2 atomic orbitals are overlapping, I am saying 2 atomic orbitals are there. So these 2 atomic orbitals, there are 2 possible ways now, either it can go constructive, either it can go destructive. So how many molecular orbitals you are getting? 2 molecular orbitals. What is that? One is BMO, another one is ABMO I can say, bonding molecular orbital, antibonding. So if it is 2, you are getting 2. If it is N, this will be N. So it means N by 2 BMOs and N by 2 ABMOs. Is this clear what I am saying? Okay. So this is very like basic things. First of all, you need to understand at least. See, I can complete this chapter only with the tricks, but basic idea you should be have on this topic. That's why I am giving these things first. Okay. Yeah. So what I told you, there is a concept called linear combination of atomic orbitals by using this psi A plus psi B. Now square this so that you are going to get a wave like this. Yes or no? If it is undergoing subtractive overlapping, the amplitude is 0 here. You can see. So now, what do we mean by node or nodal plane? Haven't heard this word? Node means the probability of finding an electron will be 0. So here, see what I told you, if greater the amplitude, this, if I say this greater this height, greater is the probability of finding electron. Electron density is maximum here. If this point, if I take, what you are understanding from this point, is there any probability of finding electron? So I can say this is a node. Okay. Now if you see additive overlapping, you are not having any node here. But if you see a subtractive overlapping, see here we have a node. Are you getting what I am saying? So now they may ask like how many nodes are possible when 1s orbital overlapped, like that. Okay. So this is basic understanding in the form of waves. So look at here, in order to form additive overlapping, see this is 1s orbital, this is also 1s orbital. Now they are indicated with the waves. If it is undergoing additive overlapping, you are getting a wave like this. Is there any node here? No. So this is what overlapping? Bonding molecular orbital is formed by constructive interference. So you are going to get a orbital like this. Like this is what now? Molecular orbital you can say, formed from combination of 1s and 1s. So I am writing it as, see, they are overlapping like this now. So this result to form a sigma bond. So that's why it is mentioned as sigma 1s. Okay. Now this is additive. What is the other way possible? Subtractive we have now. So if it is undergoing subtractive, see, one is plus sign, another one is opposite sign, minus sign is there. So now what you are going to get? A node. So in this case, see, if orbitals are of same sign, what I told you, we are going to get a constructive interference bonding. If they are with opposite sign, we are going to get a destructive interference, see, positive sign, negative sign. So we are resulting a node or one nodal plane. If this is what formed, it means this will be what? This plane is what? Nodal plane, can I say? Yeah. So one nodal plane is generated here. Okay. Or nodal point is generated here, you can able to answer. Okay. Yeah. So that is formed BMO sigma 1s I have mentioned. This is means BMO. Here it is sigma star 1s I am saying. So star represent what? Antibonding. So this is ABMO you can answer. Okay. Now like this, for every orbital, so for 1s, when two 1s atomic orbitals are combined, what you are going to get? One is sigma 1s, another one is sigma star 1s. Similarly, when 2s undergoing combination, sigma 2s, sigma star 2s. Now, if I have 2p, how many p orbitals are there? We have px, py, pz, right now. So now out of these three, consider one is internuclear axis. So let us say like three coordinates are there now. So let us say internuclear axis is like this. This is pz you can consider. So this is again pz you can consider. So this is the internuclear axis. See, xyz means how they are perpendicular to each other like this. So when they overlap like this, like a head-on overlapping we should call. So that results to form a sigma bond. If one orbital, z orbitals are along the axis, remaining should be perpendicular to it. It means that orbital will be having like sidewise overlapping like this. Okay. So head-on overlap gives sigma bond and the sidewise overlap gives pi bond. Okay, so out of these 3, one will form sigma, remaining 2 will form pi's, right now. So for pi bond formation, we have equal probabilities. Why I am saying equal probabilities? If I ask, pz forms first or py forms first? Not like px or py, both will form with same probability. Why? Because if this is the z axis, x will be like this, y will be like this. Both can be, when it is coming like this is also comes like this now. So they have with equal probabilities like this. Yes or no? So now what is going to happen? When pz overlap, you can get sigma pz and sigma star pz, right? And when other than this we have now, so that will form pi. Okay, so pi px you will get, along with this you will get pi pz also at the same time. Yes or no? So respect to anti-bonding means what? Pi star, sorry, pi py. Okay, okay, here px pi star py, like this. Okay, now this is about the normal story. Now let us take one molecule and we will do now. So for example, I am taking O2 molecule. Just tell me how many oxygen atoms are involved here? 2. Okay, what is the electronic configuration for this? 1s2, 2s2, atomic number is 8, means 2s2, 2p4. Now listen here carefully. Both of them have same electronic configuration. So 1s of this atom, 1s of this atom and this atom will overlap to form sigma 1s, sigma star 1s. Right now, how this like both came? This is also have 1s now. This one is, it's 1s. So we will be getting 2 bonding, one is, another one is anti-bond. Is that clear? Next here you have 2p4. So these 2 overlap to form these 2. Okay, and this one overlap to form sigma 2s, sigma star 2s. After this, again, how many p orbitals are there? 3. Out of that, consider any one orbital as internuclear axis. By default, I am considering z axis as internuclear axis. That will form sigma bond. So sigma 2pz, sigma star 2pz we are expecting right now. So keep this sigma star aside. Okay. After this what we have? Yeah, pi 2px, which is equals to pi 2py. After this respect to anti-bonding, what is that? Pi star x 2py. Okay. So now I will be asking you energies. If I give 1s and 2s, tell me what is the energy order? Do you remember energy order? So energy order depends for multi-electron system n plus L. Did we discuss? And for single electron n value, do you remember this? Okay. So based on this, out of these 2, which is higher energy? 2s. Similar to this, when I have, remember here, when I have 2 atomic orbitals, I have 2 atomic orbitals. So these are undergoing constructive interference to form bonding molecular orbital and destructive interference to form anti-bonding molecular orbital. See, if this is the energy coordinate, so look at here, bonding I am writing in the down, here atomic orbitals and so what is the energy order now? Here, I mean for this you tell me, next we will go here. So one is, lowest one is bonding molecular orbital, then next atomic orbital, next this is what? Energy order. Okay, I will discuss again with this. Tell me here, so out of these 2, which is bonding less respect to anti-bonding after. Then next, this will be the energy order. After this here. See, after writing sigma 2pz, I have written bonding because bonding will be always lower in energy than respect to anti-bondings. Again, so whatever, see if this is the level of atomic orbitals, whatever the depth you are seeing, same should be the height. See, if this is the lower energy, same height should be there for respect to anti-bonding. That's why I have written it as at the end here. Okay. So now this will be the having equal energies. It means what we should call these orbitals as equal energies, means you should call them as degenerate states. What is that? Degenerate states. Okay, after that this is also degenerate. Out of these two, which is lower energy? Always bonding lower than anti-bonding. So like this, and respect to here like this. Now fill the electrons as per 3 rules. What are the 3 rules? Yeah, how many electrons we have? 8 and 8, total 16 electrons are there. So 2, 4, 6, 8, 10. See here I am filling 9, 10, like one electron you should give. 11, 12, 13, 14, 15, 16, like that. Okay, so now I think we missed anything. So how many electrons are there? 8, 16, now 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16. 16 over, na? Is that clear? Everything is clear here. How many electrons are there total? 16. Just 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16. Total 16 electrons are done. Yeah. So now here if you see here, how these electrons are there here? One electron is there. Are they paired? No. So if unpaired electrons are there, it has some magnetic nature. Therefore O2 molecule is considered as paramagnetic substance. What is it? Paramagnetic. What is its magnetic moment? Mu will be root over n into n plus 2 formula you can use, given in structure of atom. Okay, how many unpaired electrons are there? 2. So n value will be 2 into 2 plus 2, so 4. So it will be root 8, means you will get around 2.83. Okay, like that. It is about magnetic moment. Now what I am going to explain you is, I just want to ask you, I am writing O2 molecule now. So how many bonds will be exist between these two atoms, O and O? That is called as its bond order. What is that? Bond order. So how many bonds present between these two O2 atoms in a molecule? So for finding bond order, we should use a formula like half into number of BMO electrons minus number of ABMO electrons. Okay, so BMO electrons are how many are there? Just count here. 2, 4, 6, 8, 10. 2 electrons, na, these are. So how many electrons are BMO electrons are? 10. Okay, so bond order will be half into 10 minus antibonding, you just count 2, 4, 5, 6. Okay, so 6 electrons here. So total how much it is? 4 by 2. So bond order will be 2. Between two oxygen atoms, we have 2 bonds like this. Okay, so what is the bond order of O2? 2. Okay, so now you got bond order, and you can able to say whether diamagnetic or paramagnetic. Okay, so O2 is which nature? Paramagnetic nature, and bond order is 2. Okay, so now you observe this one more thing. If number of electrons in bonding increases, bond order becomes, if number of electrons in bonding increases, bonding molecular orbital increases, bond order also increases. If number of electrons in anti-bonding increases, bond order decreases. Now the questions will be something like this. Now they will add one electron to, see, O2 means bond order you are saying 2. If they will make it as O2 minus 1. So what happened? How many electrons it has now? 17 electrons. That goes to which orbital? Anti-bonding it will goes. If it is going into anti-bonding, what happens to bond order? Decreases. Now it becomes 1.5. If it is O2 minus 2, tell me in this case, that electron also goes to anti-bonding. Again bond order decreases. It becomes 1.0. Now I am writing O2 plus. Removed now. So 15 electron. From where it is removed? This is also a question. Like for conversion of O2 to O2 plus, electron is removed from where it is removed? Which one it is? Pi star 2px or pi star 2py orbital electron is removed. Okay, so it becomes anti-bonding electron is removed. So bond order what happens? Increases. So it becomes 2.5. So this is the question asked previously. I will show you. Now tell me, between two atoms, as number of bonds increases, what happens to the stability? Stability increases. So I can say bond order directly proportional to, or stability directly proportional to bond order. Stability directly proportional to bond order, you can take it like this. Okay. So now between two atoms, what I am saying, between two atoms, number of bonds increases. What about its bond strength? See, this is one atom, this is another atom. Between these two, number of bonds increasing. This one bond, see 2 bond, 3 bond, like this it is becoming. So what happens? Number of bonds increases, atoms comes very close now. So strength becomes more. Effectively they are binded right now. So bond strength also increases. Stability increases, bond strength increases. What about bond length? See, initially they are like this. Now they are, as number of bonds forming like this, they are coming close. So bond length, so I just want to relate them. So bond order directly proportional to stability, or bond strength, or inversely proportional to bond length, like this. Can we make this common relation, generalized relation? Yes. Okay. Yeah. Based on this is done now. Yeah. So now you need to remember these orbital energies first of all. So tell me, what is that orbital energies we got? Just directly, randomly you tell me what is the orbital energies we got. Like sigma 1 is that one. Tell me. Sigma 1 is, star 1 is, sigma 2s, sigma star 2s, sigma 2pz. What I told you, sigma star 2pz is at the last. Next after this, pi 2px, pi 2py, pi star 2px equals to pi star 2pz. Okay. Pi star 2p, sigma star 2pz. This is what we have written. Now this order, this is energy order, valid when total electrons are greater than 14 electrons. When total electron count is greater than 14, we should use. For O2, how many electrons are there? 16. So greater than 14, now use this order. If it is less than 14, when less than 14 electrons is present, or less than or equals to 14, in both cases you should use this one, sigma. Same, tell me, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Next, after this, here what we have seen? Z. So just interchange these two things. So what is that? Pi 2px equals to pi 2py. After this, I told you to interchange these two. Sigma 2pz. Keep everything as it is, just interchange this. Next, pi star 2py, pi star 2p. Anyways, this one 2pz. Okay, so this will be the scenario when total electron count is less than 14 or equal to 14. For N2 molecule, which one I should use? N2. N2, how many electrons are there? N2, N nitrogen. 14. So which one I should use out of this? Second one. For C2. So now done now, second one we should use. Okay, it is done now. Now I will show you a few questions. Now directly we will go to the questions. Yeah. So the molecule that shows paramagnetism is, so tell me which one will shows paramagnetism here? So tell me, how can we do this? What the answer? Just follow the energy orders. So for F2, how many electrons are there? Huh? So for this 18, okay, 18 means what is the order? Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma z, pi 2px, pi 2py, next pi star 2px, 2pz, sigma star 2pz. Like this, after writing 18 electrons now, so fill here 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. All electrons are paired now. So it is diamagnetic. So it is not our option. So like that, verify for these three. Now verifying for these three is very easy. Because why? All of them are what? See, N2 less than 14 or equal to 14. B2 10 electrons only, 12 electrons only. Now you can have only one order. So what is that order? Tell me. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz, pi star 2p py, next sigma star 2pz. Okay, so fill the electrons. 2 for N2 will do 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, sigma only now. So 2. See, this is the energy order, right? Like this. So in particular energy you should fill the electrons. If they are degenerate, then only give one electron like this first. Okay. So is this diamagnetic or paramagnetic? Diamagnetic. So N2 dia. So what is the bond order of N2? Bonding electrons minus anti-bonding electrons by 2. So you will get 10 electrons. See, 2, 4, 6, 8, 10. 10 bonding, anti-bonding are just 4 electrons. That's it now. 10 minus 4, 6 by 2, 3. So that's why N2 you are writing like this. Okay, is that clear? Okay. So now I will tell you the trick for this anyways. For this question you tell me, B2 how many electrons are there? 10 electrons. So it means 2, 4, 6, 8, 9, 10. It means how it is? You should fill the electrons something like this. 8 over 9, 10. So paramagnetic with 2 unpaired electrons. Now you will get some magnetic moment value also. So your answer should be B2. Okay. So now for C2, 6 plus 6, 12. So 10 over 11, 12. Diamagnetic. Is that clear? Okay. So now one more thing, very important thing here. See, your answer for this question is done. B2 is done. Now my question is, what type of bonds present for N2 molecule? Now you just have written for N2 bond order as 3, like N triple bond N. Okay. So what type of bonds these are? And in C2 also you got what is the bond order for C2 and B2. Just try to calculate this. This is the extra question. I just want to make you clear with the concept. That's what I am asking. So N2 bond order you got 3. What type of bonds these are? 3. See, 12 electrons over, 14 electrons over. So now look at here. Bond order formula if you observe properly, half into BMO electrons minus ABMO electrons, anti-bonding electrons. So now for every BMO and ABMO, if they are same numbers, what happens? Bond order becomes 0. See, this one, can I remove? Again. This one, can I remove? Bonding, anti-bonding. Again, these are bonding electrons, these are also bonding electrons, no respect to anti-bonding electrons to cancel. It means total bonding electrons are how many now? 2 plus 2 plus 2, 6 by 2. So that's why 3, bond order 3 we got here. So now how many, see, one bond means how many electrons? 2 electrons. So here you have 2 electrons in sigma, so there is 1 sigma, 2 pi's, these 2's are pi bonds. Is that clear what I am explaining? Okay. In case of N2 you are saying there is 1 sigma bond, 2 pi bonds. Similarly, I want what kind of bonds present for C2 and B2. Find bond order for C2, B2 and respective type of bonds. C double bond C, okay. But what type of bonds these are?
1 sigma.
Once again re-look into it. It is already there. 12 electrons means where it will stops? Here itself, right now. So all these are removed. Okay. So you are remaining just with
Only 2 pi.
electrons in pi orbitals. So 2 electrons in one pi orbital, 2 electrons in another pi orbital. So both bonds are pi bonds. Generally what we think?
1 sigma, 1 pi.
Like bonds between two atoms will be 1 sigma and 1 pi. But in C2 molecule you have bond order 2 and both bonds are pi bonds only. They will ask a question on this kind of molecules also. Okay, is that clear? Okay. Now tell me for B2 also.
2, 4, 6.
B2 means 10 electrons. Fill now.
9, 10.
Again, but what is the bond order you got first?
Bond orders. Bond orders.
So 8 electrons over up to here, 11, 10, 9, 10, 10 over. So these are over. So you have electrons in bonding molecular orbital but 2 electrons. So 2 by 2, 1. So bond order will be 1 here. So between BB you have 1 bond. What is the type of bond? It is pi bond, not a sigma bond. Is that clear? And it is paramagnetic. Okay. Now question will be like this. Which of the following is are paramagnetic in nature? Write the question otherwise. Which of the following is are paramagnetic? Which of the following is are paramagnetic? I hope you have multi-selective questions right now. From chemistry also you can expect. Okay. So which of the following is are paramagnetic? Option A, C2. Option B, B2. Option D, option B over now, C, O2. Next option, option D, Cn minus.
Cn minus.
Cyanide ion. Tell me.
Paramagnetic.
Just filling only. Count number of electrons, fill in that. That's it.
One is B2 as
BT just now I told you. B2. Next. O2 also I discussed. Anyways.
O2 and C2 are diamagnetic. O2 and C2 are diamagnetic.
O2 and
C2.
O2. Once again check, cross verify it. That is our first example. O2 is paramagnetic. How many unpaired electrons?
2, sir.
2. So options are B2 and
O2, sir.
B2 and O2. Remaining 2, just count number of electrons.
C2 is 12, sir.
12. So already seen here,
6 and 6, sorry.
fully paid, all paid. Now N, Cn minus how many?
14, sir.
When you have 14 electrons, for N2 what you have seen? Diamagnetic or paramagnetic? N2, that's what. So when you are doing some examples, try to remember that standard example like N2. What you have seen? See 12 over 11, like 13, 14. So 14 electrons are filled. All of them are
Filled, sir. Completely filled.
paired. Now 14 electrons are paired. So no unpaired electrons, diamagnetic. Is that clear? Okay, just try to remember these two energy orders. Greater than 14 means this will be the order. Less than 14 or equal to 14 means the second one will be the order. If you are clear with this, you can solve maximum number of questions. Now, what are the applications I have told you? Applications. Applications of MOT. Let me tell you. Yeah. So, you got to know how to calculate bond order. What is the formula I told you?
Yeah.
Half into BMO electrons minus ABMO electrons, that's it. Okay. After getting bond order, you can able to arrange them in the bond length right now. So how they are related? Bond order inversely proportional to bond length, that is done. Bond order directly proportional to stability. Bond order again directly proportional to bond strength. And if bond order is equals to 0, it means between two atoms, if there is no bond, will they exist as a molecule? Between two atoms, if there is no bond, will they exist as an atom, a molecule? No. So it also says about existence of a molecule. If bond order is 0, molecule does not exist. Right now? If bond order greater than 0, molecule exists. Molecule or ion will exist. Molecule like bond order less than 0, will it possible? No. Always filling will be taking place in BMO, after then only ABMO. It means BMO electrons are present, bond order will be definitely like possible. Okay. So next, it also says about paramagnetic, diamagnetic you are saying, also finding its spin magnetic moment like root over n into n plus 2. Okay. And color, how this will be says as color. So for example, here where we discussed this one, here we are discussing now. So let me take one more page. So for halogens, let us say F2 like this. So tell me how many electrons we have? Sigma 1 is sigma star 2s, sigma star 2s, sigma next sigma 2pz, next pi. What reverse? F2, 18 electrons.
Pi 2px is equals to pi star pi 2py. Pi star.
See, some books will give like this, sigma 2pz, instead of taking 2pz, they may take 2px also, then take z here, that's it, no issues. Any of the three axes, one should be internuclear, remaining should be perpendicular. The perpendicular one become pi, internucleus becomes sigma, that's it. Okay. After this, pi star 2px, okay. So 18, 2, 4, 6, 8, 10, 11, 12, 13, 14, 16, 18. Okay. Just I know the electron, that's why I feel like this. But whenever there is degeneracy, you should fill 1 electron, like maximum multiplicity given by Hund's rule. Okay. Yeah. So now just count. What is the bond order?
2, 4, 6, 8,
18 electrons means
10 might be
10 will be bonding. See, there are
10
total 20 molecular orbitals you are seeing here. 10 bonding, 10 anti-bonding. So out of that, one is anti-bonding is not filled. From this you can able to know, get to know now. So 10 will be like 10 orbitals are BMO, 10 orbitals are ABMOs here. So all BMOs are filled
So 10.
like that. Yeah, is that clear? Total, just count man. See, 2, 4,
6, 8, 10.
10 BMO electrons, remaining are ABMO electrons, like that. Okay. So what is the bond order you are getting? 1 here. Okay, this is fine. I am not talking about bond order, you know about this. So I am just wanted to discuss about the highest energy orbital here. What is the highest energy orbital?
5 star to pure.
These are degenerate now. So these both are highest occupied molecular orbitals. What I am saying? Highest occupied molecular orbital. These are occupied by electrons now. So highest occupied molecular orbital. So you should say homo orbital these are. Okay. And tell me what is the lowest unoccupied molecular orbital? Lowest unoccupied. See, this is the energy order. Where do we have unoccupied orbital first? This is the only one. All these are occupied. If we have any other orbitals, that will be also this side. That will be also unoccupied. But lowest one is this one only. So you should say this as lowest unoccupied molecular orbital. This is HOMO, this will be LUMO. Okay. Now electronic transition takes place from this HOMO to LUMO. So due to this reason, halogens exhibit color. Okay. So what is the reason for color? HOMO-LUMO electronic transition. Okay. Like fluorine, chlorine, they will show, bromine, they will show color. Iodine, you are seeing violet color now. Okay. So they will absorb low energetic waves, wavelength, and emits high energetic wavelength. They will absorb yellow color wavelength and emits complementary color, violet color. Okay. That's why you are seeing it as violet. Clear? The color property is also clear. What are the applications are given?
One is bond strength and bond length.
Tell me.
Stability. One is stability, sir. Another is
Fast.
and then
Bond order, bond length, bond strength, magnetic moment, color, and existence of a molecule. Okay. So now look at here. So tell me order of the stability for this. We did already for this. Just tell me fast. See, if you remember, when I told you 14 electrons in nitrogen case, what is the bond order you have seen? 3. Okay. If I have 13 electrons only, you are removing electron from bonding molecular orbital. So that becomes, if it is like 13, let us say 12 here, so it will be 2.0. If it is 11, like this. Okay, decrease 1 electron, decrease 0.1, 0.5, like 0.5, order also, bond order also. Now increase 1 electron, 15th electron goes to anti-bonding, so it becomes what? Going electron where that 15th electron is going?
electron transition happens, sir.
Anti-bonding it is entering, so what happens to our bond order? Decreases. Again 2.5, if it is 16th electron, like this. Now just count the number of electrons here. So for O2, 16, we know bond order for this is 2. Okay, for this one 15 electrons, bond order will be 2.5, like just look at here. And for this 17 means 1.5. Why it is 1.5? It is new electron is entering into which orbital? Anti-bonding. That's why bond order is reducing here. Okay, it is 1.5. This one 1.0. So based on that, more is the bond order,
More is the step.
stability. So which is more stable? O2 plus. Okay, where do we have O2 plus? They are asking increasing order of stability. So which option is correct? Yeah, that is the correct option. Like, see, that is properly I have taken normally, but see, they are properly arranged. 1.0, 1.5, 2, 2.5. That is increasing order only, no? So that will be our answer. Is that clear? Okay. So bond length, if they ask?
Bond length.
Yes, inversely means what is our option? Tell me here. So I will write. Bond length will be more for O2 minus 2, then next O2 minus, then next O2. This will be the bond length order. If they ask bond order or bond strength or stability, you should be answer with this. Next, this one. This one. This one, tell me. KO2 it is there. Okay. Now tell me, what is the nature of potassium? Which group element? Metal. So whenever it is combined, it always gives its one electron. So it becomes K plus. If it is K plus, this should be O2 minus 1. So O2 minus 1. These are the statements for O2 minus 1. Read this. So O2 minus 1 means what is the oxidation state of each oxygen atom here? 2 oxygen has minus 1. 1 oxygen will be half. Which half? Minus half. In superoxide, what is the oxidation state of each oxygen? Minus 1 by 2 you should say. If it is peroxide, hydrogen peroxide you are saying H2O2. So in this case it is O2 2 minus. So each oxygen will be having minus 1 and minus 1 charge. Normal oxide like water is an oxide, like sodium oxide I am saying. Here oxygen will be with a minus 2 charge. Got the difference? Oxide means O minus 2, superoxide means O2 minus 1, peroxide means O2 minus 2. Like peroxide. Hydrogen peroxide you know now. What is the formula? Remove the 2 hydrogens. O2, 2 hydrogens as H plus. So O2 2 minus. So O2 2 minus. Like that. Remember, try to remember that. Now read this statement about superoxides. Oxygen is paramagnetic and has 2 unpaired electrons. In superoxide, they are saying oxygen is paramagnetic. Is it correct or not? You have written it for twice for oxygen only. How many unpaired electrons are there in oxygen molecule? If it is oxygen molecule, we have 16. Now, but they are discussing about minus superoxide. So 17th electron. That 17th electron is pairing up right now. So how many unpaired electrons we have? 1. But they are saying 2. So remove it. Next, bond order is 2. Is it 2? For 16 electron bond order 2. That 17th electron bond order is, so this is also incorrect. Next, the bond order in superoxide is, so this is perfectly correct. Next, superoxide is not paramagnetic. It is paramagnetic with 1 unpaired electron. So this is also incorrect. So option 3 will be our answer. Is that clear? So now look, any other question is given in the exam. So this one is there, you can easily solve that. I have that confidence. So just look at that and try to answer. Just isoelectronic means same iso, same electrons. So count Cn minus carbon 6 plus 7 plus 1, 14 electrons. NO 7 plus 8, 15 electrons, that is not the one. Here Cn minus 14, CO 6 plus 8, 14. So option 2. Is that clear? Okay, verify other options also if you want. Any other thing is missing here? No. All the questions are over from your BT question paper. So I just want to give these questions as a homework. I mean, just for practice purpose. Just look at this. Same, you feel like same way as you solve the previous question. Take the screenshots of this and this one and this one and this one. This one will be the, see, I given the table. Do you remember that 14 electron 3, 15 electron 2.5 bond order, something like that. See, there is one exception. With 13 electron, I have told you bond order will be 2.5. So there is one exception if there is CO plus molecule. Okay, so it has 13 electron, but it has bond order of 3.5. This is an exception you should remember. For all the other 13 electrons means for only CO plus
3.5.
yeah, remember this. Okay, next. Try to solve these questions. Okay, yeah, anyways, I will explain this dipole moment in the next class. This one also I will tell you. Yeah, these are the questions in BT, JAM BT related to chemical bond. Okay, I hope you have completely watched this session, those who are in the live. Okay, so thank you for watching. Stay connected with this channel. We'll meet in the next session. Thank you. నాకే బోరింగ్గా ఉంది అసలు చెప్పడం.